feel like that one should be on. Okay, I'll give it a minute. So, it's like doing the slow warm up. So let's step back and review the bidding for a moment. We're in Chapter 3. This is the last lecture in Chapter 3. This chapter has been about doing steady state circuit analysis with impedance-based modeling. So we can stay completely algebraic, although we have to use complex algebra, which is a little bit more challenging. But no differential equation solution, but we don't get the transient response as part of our solution, right? Which in many cases is just fine, so that's why we do it this way. But sometimes we want the transient response, like in your homework problem this week. You want that transient response. Just to give you an idea of what it should look like when you graph it. So you've got your graph of the response. The response should look, I don't remember what the initial condition is, but the response should look like a sinusoid that there's a high frequency, the one that's damping out early, and then it turns into the steady state one. So that's roughly what you should be looking for. I expect that it's presenting some challenges. I've heard some questions from people, but I think that the key is not to get bogged down in the algebra, the math. That's the real challenging aspect of the problem. There's really nothing conceptually different than last week's problems that you solved. It's just with a sinusoidal input and an underdamped. If you're not getting an underdamped response, you've got the wrong solution to your characteristic equation. So it should be oscillatory, both in transient and in steady state. But in transient, it should be a decaying sinusoid. Steady state is just a sinusoid. Okay? All right. Good. So now we're going to learn how to do this steady state analysis. And you know how the stuff we presented last time, that methodology is pretty straightforward. It's mostly just algebraic. Combining things, not too bad. Just as with resistor circuit networks, though, there are common themes that show up. Like you see voltage divider circuits a lot, and then current divider circuits a little less frequently. And so there's an application of the same concept of voltage divider, current divider, that allows us to skip working through the elemental equation, the continuity, and KCL, KVL, etc., and just jump right to the answer, essentially. And then you just got to combine the impedances. So that's what we're going to do today. So it's just like a shortcut to the same solutions we would have gotten out of the procedure from last lecture. Okay. So in lecture 1.2, we developed the useful voltage divider formula for quickly analyzing how voltage divides among series resistors. This can be considered a special case of a more general voltage divider equation for any elements described by an impedance. After developing the voltage divider, we also introduced the current divider, which divides an input current among parallel elements. We didn't talk about that when we did resistor circuits, but there is one in resistor circuits as well. But I thought we would wait for this moment that we're in right now. So, voltage dividers. First, we developed the solution for the two-element voltage divider shown in this figure. So, we've got a voltage source of some sort, Technically, this could be any voltage coming in. It doesn't have to be a source. Say you just have some voltage that is coming in right here from the network. The same holds true no matter where you are. But in the simplest case, it's just a voltage source connected to two series elements. And those two elements are represented by Z1 and Z2, just impedance 1 and impedance 2. So it could be resistors, could be inductors, could be capacitors. One could be a resistor, one could be a capacitor. Doesn't matter. We can represent any of those elements by impedances, right? So that's why I just put these boxed elements there, just some generic element. We choose the voltage across Z2 as the output. So we're going to say this is our output voltage. And we're going to analyze the circuit using our usual methodology, and we're going to derive the voltage divider expression. Okay? So we'll go through the analysis. It's pretty straightforward, but we'll walk through the steps. So step 1, circuit diagram's already given, so we don't need to draw it. Step 2, the assumed direction of positive current flow, they're already given. So 3, the elemental equations are just generalized Ohm's law equations, right? So we need to write an elemental equation for the Z1 element and for the Z2 element. So what is the elemental equation for Z1? We'll just use subscript 1. What's generalized Ohm's law?
V1 equals I1Z1.
Great. So V1 equals I1Z1. So we've got Ohm's law, generalized Ohm's law for element 1. And what does that make Z2's elemental equation?
Same thing, just subscript 2.
Great. Okay. That's done. The KCl equation, there are 3 nodes here, right? 1, 2, 3. These 2 nodes are connected to a voltage source, so we don't need to do KCl on those. This one is connected to these 2 elements, so it says what about the current I1 and I2?
They're the same.
They're the same. Yeah, so I1 equals I2, or I1 minus I2 equals 0, or I2 minus I1 equals 0. They all just mean I1 equals I2. The KVL equation, so there's only one loop, right? So yeah, so if you wanted to write, since we want to solve for V2, let's write it in terms of V1. V1 equals, because that means that we're going to eliminate V1, and that's what we want to do. So let's write V1 equals, it's going to be Vs minus V2, right? And if you ever get confused as you're going around that loop, like, what's the sign? Just like start somewhere and just go around and say, okay, drops are going to be positive, so V1, V2 plus V2. And then, oh, this isn't a drop, this is a gain for me because I'm going this way across it. So minus Vs equals 0. You can always go back to that. So if you get confused about just like jumping to the solution up to the variable you want, always just go back and go around the loop, counting drops as plus and gains as minus. Or you could even do it the other way, where drops are negative, gains are positive. Since you're setting it equal to 0, it actually does not matter. You always multiply everything by -1, and the signs work out. So we've got 4 equations, right? 4 equations, and we want to solve for V2. So let's eliminate I2 and V1 using these two, the KCL and KVL equations. So we rewrite our table, Z1, Z2, and we say, okay, Z1, we want to eliminate, we said V1 from this. So we're going to say I1 equals V1 over Z1, which V1 we're eliminating using the KVL equation. So Vs minus V2 divided by Z1. Z2, we said we're going to eliminate I2. So we can write the Z2 equation as V2 equals, instead of I2, we're going to insert I1, Z2, and that's we've succeeded. So then all we want to do is eliminate I1, and actually I1 is, this first equation has I1, the second equation has I1 there, so let's substitute the first equation into the second equation. So we get V2 equals, instead of I1, we have Vs minus V2. And it would be over Z1. I'm going to pull out the Z2 over Z1 factor. And go to the next page. We want to solve for V2, right? So we've eliminated everything except for V2 and Vs. Vs is the source. Go ahead. So we need to bring the V2 term from the right-hand side to the left-hand side, right? So we bring it over, we factor out the V2, we divide what's left over again. You guys might be noticing a pattern here. We keep doing the same operation. We end up with V2 being equal to Z2 divided by Z1 plus Z2 times Vs. So this is the two resistor, or two element, I should say. Two element voltage divider equation. It tells us what the output voltage V2 is in terms of Vs, and then notice that it's the same exact thing as the resistor voltage divider. You put in the impedance of element 2 divided by the sum of the impedances. So same thing, except for instead of resistance, you put in just whatever the element's impedance is.
And that could be anything, like a light bulb?
Yeah, a light bulb would be a resistive element. They don't act very linearly though, because they heat up really significantly. So old filament light bulbs, at least. New light bulbs are like a whole thing because they have their own little drivers in them and stuff. So yeah, they don't behave like the old light bulbs do. I bought some old, because I had an old lamp that couldn't use a LED in it, so I had to go find filament bulb.
The ones that are like going out of business.
Yeah, well, they still can make them, but I don't know what the laws are. I think they have to charge a significant amount for them. Yeah, they're like, I don't remember. It was like $10 a bulb, something. It's insane. I was like, oh, it's so painful.
They created like wattage laws.
They did.
So yeah, like you can't go out and buy like a cheap $2, 60-watt bulb or whatever, 100-watt bulb.
Yeah.
Like
Yeah. Which is, I mean, it's fine. I didn't actually. I wanted to use LED in it, but I just couldn't because the lamp wouldn't run it. So I tried the LED in it and it wouldn't work. So I had to
One
use
of those
it.
losses, my dad bought a whole like case. of
Stockpile.
stockpile.
But I will say, I mean, it's only like, I think it's like 20 watt or 30 watt maybe bulb. Like, it's really not much, but it's just in like one of those little like desk lamps. The thing gives off some heat. I'm next to it and I'm like, whew. Compared to the LEDs that I've gotten used to, it's just a lot of heat, which is why we use LEDs because we really aren't trying to run heaters in our lights, usually. Unless we literally want to have a heat lamp, in which case we do. But so this is the same equation that we're used to, but with impedances in it. So let's look at the N impedance voltage divider. So for output VK, so the voltage across the kth impedance, across the impedance ZK in series with N impedance elements with input V in, we can just write that VK is equal to the impedance of the kth element, ZK, divided by the sum of all of them. So Z1 plus Z2 plus, including ZK, plus all the way up to Zn multiplied by V in. So the same as the resistor and resistor series voltage divider. It's the same form, it's just with impedances, which is nice. It gives us a shortcut to solving a lot of problems. As we'll see, we're going to do an example at the end of today, and it's going to be like pretty easy to do, even though if we had used the methods of last chapter, it would take probably a couple hours. So. All right, current dividers. By a similar process, we can analyze a circuit that divides current into N parallel impedance elements. So for output IK, so the current through the kth impedance element through the kth impedance in not series but parallel with N impedance elements with input to those parallel impedance elements I in, we get that the kth current through the kth element, that's probably a better way to say it, is 1 over ZK divided by 1 over Z1 plus 1 over z2 plus 1 over zk plus 1 over zn, all of that times I in. So it's very analogous to a voltage divider, but there are some key differences. This is for elements in parallel, not in series. So that's one key difference. This is for dividing current and not voltage, another key difference. And then also, all of these, instead of just being the impedance, it's the inverse of the impedance in this equation. We haven't used the term, and I'm not really going to use the term, but just so you're aware, 1 over the impedance is sometimes called the admittance. So this is, you could think of this as being the admittance of the kth element divided by the sum of the admittances of the other elements. But I just have always felt like that was an unnecessarily I guess just this superfluous definition. Didn't really need to be there. We can just say the inverse of the impedance, and that's fine. All right. So we have an example. Voltage divider with impedance. So given this circuit with a phasor form of our sinusoidal voltage source, Vs, and output the voltage across the inductor, VL, what is the ratio of output over input amplitude? And what is the phase shift from input to output? So this is a little bit like your problem in your homework, asking for the ratio of the amplitude from the input to the output. It's essentially you have to solve for the output amplitude to find this ratio. But it's another way of thinking about it, so I thought I'd give a little variation on what we're solving for instead of just always the output voltage. Yeah?
When you use the term amplitude, are you referring to voltage?
So it depends. I'm going to refer either to the voltage or the current amplitude. So in this case, the voltage source is sinusoidal. So this input amplitude is a voltage amplitude. So it's like 20 volts or something like that. But AC, 20 volts. And when you have a sinusoidal voltage, you're going to have a sinusoidal current too. So they both are going to have amplitudes. So it just depends on the context. If I say the amplitude of the input and it's a voltage source input, then it's going to mean it's a voltage amplitude. If it's a current source, then I'll mean a current amplitude.
But none of that applies to DC.
Right, DC, there's no amplitude really. I mean, you can think of it as being like a zero frequency amplitude. Sometimes we do talk about it like that, but it's not sinusoidal, right? So there's no real amplitude. So those are the two. I mean, the two typical sources are going to be DC or AC, right? Sinusoidal. Technically, there can be others, but just not as common. We don't see that very frequently. Yeah. So this one, we've got our problem set up. So considering we just introduced voltage and current dividers, we should probably use them, right? So we could go through our steps, right? Our 1 through 6 steps. But turns out we don't have to, because we can make this an equivalent impedance by combining them in parallel, right? And then we can see that this is then just a series impedance between this resistor and then this combined impedance. When we combine these two in parallel, we don't lose the voltage across it, which is the output that we're interested in, right? So the voltage across this equivalent impedance is going to be still our output voltage. So we can actually do this in one line, but I will use two to write it. So we'll call this ZR, the impedance of the resistor, and we'll call this ZE, the equivalent impedance of those two. And then we can write down what the voltage divider says our output voltage is going to be from the voltage divider rule immediately. So we can say that our, so VL, which is our output, is equal to, it's the impedance of the equivalent impedance of those two parallel impedances divided by the sum of the resistor impedance and the equivalent impedance. And that's all multiplied by Vs. Okay, did you see that move? Okay, so there's, yeah, one impedance, another impedance. They're in series, so it looks exactly like our, where is our, yeah, our voltage divider, two element voltage divider. So we just use that formula and boom. And what's nice is we're looking for the ratio, really, of the output to the input. So we can just divide Vs over to this side, and it's just equal to ZE over ZR plus ZE. So the rest of the problem is just simplifying this right-hand side. Okay, we're going to get both the amplitude ratio and the phase shift from this right-hand side, because that's what the phasor keeps track of, the amplitude and the phase. So we can do ZE kind of on the side over here, maybe. Maybe it's easier to work with it separately for a moment. So ZE is going to be equal to, what is the impedance of the capacitor? So this is, we can use the formula, the parallel formula, right? So we need to multiply the impedance of these two in the numerator and then add them in the denominator. That's the parallel formula. So I'll just write it ZC, ZL divided by ZC plus ZL. So ZC, ZL is, so ZL is J omega L, and ZC is J omega C in the denominator, right? 1 over J omega C. Similarly, here we have 1 over J omega C plus J omega L. We can see that in the numerator these two J's cancel, right? And the omegas cancel. So in the numerator we just end up with L over C. In the denominator, we have these two terms. We'd like to combine them. If we multiply this first term by J over J, we can add them, right? Because then they're both imaginary numbers.
Question.
Yeah.
Why did we not, in the denominator of the line above, put J, we put 1, the denominator of the second line, why did we not put JWL under
Right here.
The right term. Right.
This one.
Yeah. Am I missing something?
So the impedance of an inductor is J omega L.
And then that's
Yeah, and the impedance of the capacitor is 1 over
Oh, I
J
see.
omega
I
C.
see.
Yeah.
Just forgetting my definitions.
That's cool. It's cool. It's Friday. I almost wore a t-shirt today. Classed it up with the flannel though.
Not even something.
Yeah, I know. I was looked outside. I was like, it's raining. Not feeling it today. Like I'm just gonna. And then I was like getting ready. I was like gonna put on my boots, and I was like, rain boots. Yep, rain boots today. It's Friday. I can get away with it. So, yeah. You guys know there's a website, and it's called. You play a game. It's like 10 questions, and you have to identify it's a photo. It's hobo or professor. They just show you a photo, and you have to decide if it's a hobo or professor. It's pretty bad, but also I think I only got like 7 out of 10. So yeah, we aren't known for our great dressing habits, but it's okay.
It seems to be pretty good in the engineering department.
Yeah, it is. I would say most engineering departments are usually better. The old school engineering professors would always wear like the white dress shirt and tie to teach every time. I haven't been so great about that, but I do actually probably dress up more than anybody else in the department. So, yeah. Just saying. If anyone's keeping track, I'm winning. So this first term is going to be negative J over omega C. So we can combine these two, factoring out the J, and we get omega L minus 1 over omega C. Flip-flopping the terms. And then if we wanted to simplify this more, I would multiply it by J omega C over J omega C, because that'll bring the J to the numerator, and the omega C is going to cancel this one and simplify this as well, so I think it'll get a little nicer. That'll give us negative L omega, the C's cancel. There's a J up there too. Negative J L omega divided by, J's are gone, we get L C omega squared minus 1. Yeah, I think that's right. So yeah, so that's good. So we kind of simplified this over on the side because we're going to plug it in, and it's going to be a little easier to work with if it's simplified before we plug it in. So let's just take this and plug it in for ZE in this equation so that we get equals. So our ZE shows up in the numerator and the denominator. Therefore, I'm going to take this denominator from the numerator and drop it down and distribute it through, okay? So let's see if you can hang with me on this step. Negative J omega L, so that's the numerator of this term, right? And then we're going to take this denominator and we're going to drop it immediately to the denominator of the other, to this fraction. So we're going to have ZR, which is just R, times whatever that denominator was, which was LC omega squared minus 1. Okay. Now the other term is ZE, but the reason I dropped that denominator immediately is that the denominators cancel in the CE term now, right?
Would that be a plus? R is ZR plus, or are you distributing it?
I'm distributing it
Oh,
already.
alright,
Yeah,
okay.
I know, right? Yet another algebraic step all in once, and it's fun. Otherwise, you got to write a lot. I don't think we like that. I just like not to. It's better not to. I mean, I know that you've had professors telling you for years, write out every step. It's just that it would be so many pages of writing. We don't have time for that. So we just have the numerator left again, and it's negative j omega L. Yeah. So
So, sorry, why would that cancel if it's an addition?
so what we did is we took the denominator here, and I'm gonna call that D for a second, and we put it into something so that it's like negative j omega L over D divided by R plus negative j omega L divided by D.
So you break
I
it down with the D.
Drop the D down here so that I get negative j omega L divided by negative j omega L, or no, sorry,
R
divided by R times D plus negative j omega L divided by D, and then you got to distribute the D again, and the D's cancel. So that's why I could get rid of that D, the denominator. It's not that I can see 10 moves ahead in every algebraic problem that I do. It's just that I've done this algebraic problem 50,000 times. So when you start to see it a lot, and you start to see patterns emerge, and you see, oh, whenever you divide this thing, a fraction by a fraction that has that in the sum, you immediately drop that denominator and you get that cancellation every time. It always happens. You always get, whenever you have a voltage divider and you have a fraction as your impedance, immediately dropping down the denominator always cancels with the other term, just by construction. So, okay, so we're almost done, but we should rewrite this in terms of, we still have a fraction of
Phaser mixed with regular.
yeah, well, actually, they're both rectangular, but they're both complex numbers, right? So we like to, we want to get it in terms of a magnitude and a phase eventually. And there are different ways of combining these. So if in rectangular form we could do it, we could just say, oh, let's multiply by the complex conjugate of the denominator divided by the complex conjugate of the denominator. That will rationalize this complex fraction and give us only a complex number in the numerator. There's that way, or let's do it the phasor way. I think the phasor way is actually easier in this case. I think it's usually easier. So let's say, well, this is going to be equal to, and actually, let's do one more simplification because we can. Let's multiply this whole thing by j over j, because we have this negative j in the numerator, and we could get rid of that if we multiply the whole thing by j over j. So just for fun, just to make it a little easier on ourselves, we're going to say, okay, so j over j, so j times j is -1, right? So that makes us positive. In the denominator, we're going to take this term and move it to the front because it's going to become the real term. So j times j is -1, so that gives us positive omega L. And then we're going to have plus j r LC minus, or LC omega squared minus 1. This just makes it a little bit nicer to work with. And now let's turn them into phasors. So I'm not being very compact, which is fine because we have the whole page. So we have omega L e to the 0, right? That's just a real number in the numerator. E to the j0, I guess you could say, j0. Divided by, we're going to use our nice little trick of just calling this some magnitude e to the j some phase. We'll define them, so m1 and phi1. And that lets us write this as a single, combining these phasors, omega L over m1 is the magnitude, just dividing the magnitude, and the phase is just negative j phi1, because it has to come up to the numerator. So that is our, pretty much our solution, but we should write where m1 is equal to the square root of what?
The sum of the squares of the impedances.
Yeah, so of this term and this term, right? So omega L squared plus R squared, and I'm going to just put LC omega squared minus 1 squared. Whee! Oh. Okay. And the phase is the arctan of what over what? It's imaginary over real, right? Well, which is the imaginary part? We're taking, it's of this, right?
Isn't the J R LC what makes square minus 1? That's the imaginary part.
Yeah, so everything without the j. So everything's multiplied by j, but not j itself. So r times LC omega squared minus 1. That's the imaginary part. And the real part is just omega L. So that's our phi 1. So this is the solution, this is the phasor form of the ratio between the input and the output. If we want to know the amplitude ratio, all we need to do is read it off of this. So we can say amplitude ratio is just omega L divided by m1, which just came from right here. That's the amplitude ratio. Because what we have here as a solution is VL over VS, right? So whatever the amplitude of that is the amplitude ratio. The phase difference between VL and VS is negative phi 1, right? Phase difference. Negative phi 1. That's it. Pretty, I mean, it's relatively easy as long as you're understanding conceptually what's going on. The algebraic steps are pretty straightforward, right? So, and I think conceptually, nothing too crazy is going on. We're using the same thing. You know, we could have done this all with the same method that we learned last time, right? But we chose a sort of shortcut, or we didn't have to write down all of our elemental equations and all of our KCL, KVL. We just jumped right to that solution. So it's like we did steps 1 through 5, just using the voltage divider rule. And then we skipped to step 6, and we had to insert all of these impedances and stuff. Well, 6 like B or C. I think 6C we skipped to, essentially. So, and then instead of having to solve for VL, up to this point I kept having to solve for VL, right? But the nuance to this problem, one of the nuances, was that instead of solving for VL, you're solving for the amplitude ratio and the phase difference. So the only difference from our usual solution method was that we had to divide the VS over, which actually made it easier, right? We didn't have to plug in our phasor form of VS ever in this problem. We didn't have to plug in the given A e to the j phi because we're looking for a ratio. And we could have plugged it in over here, and then we would have had to divide by it too, again. So
Can you slide down this?
we didn't go through all of that because we didn't need to. All we needed was the ratio and the phase difference. So pretty much this is the answer to the question, how does it change? How does the amplitude and phase change of this signal when you put it into the circuit to how you get it out? So sort of like boiling it down to brass tacks, mixed metaphor. And that's actually usually one of the main interests is what's the ratio or what's the difference. We'll talk more about it later. So have a good weekend. Good luck on your quiz. Should be up around 1-ish, lunchtime.